Right, so welcome back everyone. So this lecture we're going to continue talking about sorting algorithms. So last lecture we covered the elementary sorts, talked about bubble sort, insertion sort, selection sort, shell sort, and we also talked about merge sort, which is a divide and conquer recursive sorting algorithm. Right, so this lecture we're going to talk about quicksort, which is another divide and conquer sorting algorithm, and then we'll also go on to discuss non-comparison based sorts, which are sorts that don't rely on comparisons between items. Okay, so what's the motivation behind quicksort? Right, so the thing with merge sort is that it uses a very simple split operation, right, which is also quite unintelligent, right, because it just splits the array into two halves, recursively merge sorts each half, and then, so we have someone coming to help us resolve this loud fan noise at the front, so we'll just let it help.
Oh, is it then? I don't know if there's much I can do right now. I might have to just work with it. Yep. I'll just see how it is. Could be that it's probably just needs to be shut down at the end, that's all. There's really not a lot I can do about that noise. Go at this stage and get a quick fix. Okay, I'll just have that look at that. Okay, cheers. Thank you.
All right, so continuing on. So merge sort uses a very trivial, very unintelligent split operation, right? And what that does is it causes the merge to do most of the work, right, in the algorithm. Right, so we saw that merge sort had a very simple function. The merge sort function is very simple. It just calculates the midpoint, then recursively calls merge sort, and then calls merge, right? But merge is where the majority of the work happens, right? So the question is, can we split the array in a more intelligent manner so that after we've recursively sorted, both halves of the array, we don't have to do as much work, right? So for example, what if we try to make sure that when we split the array, all the elements in the left side of the array are less than or equal to all the elements on the right side of the array, right? So that's what quicksort does, and quicksort was invented by this guy, Tony Hoare. So you've probably seen him because he was the answer to one of the quiz questions. So what does quicksort do? Well, it first chooses an item to be a pivot. So what pivot means we'll explain later. So it chooses a pivot from the array, and then it rearranges or partitions the array so that all the elements to the left of the pivot are less than or equal to the pivot, and all the elements to the right of the pivot are greater than or equal to the pivot. All right, and after it's done that, the pivot just stays where it is, it just sits where it is, and we recursively sort each of the partitions. All right, so here's a visual depiction of that process. Right, so in this diagram, we are simply picking the first element of the array as our pivot, and there are different strategies for selecting a pivot, which we'll talk about later. But here, we will just select the first element as the pivot. Then we partition the array. So after we've partitioned the array, the pivot will be in the middle somewhere, and all the elements on the left will be less than or equal to the pivot. All the elements on the right will be greater than or equal to the pivot. All right, and both of these partitions, they are unsorted, right? So what we'll do next is recursively quicksort each of the partitions. All right, and after we do that, the array will be sorted. Okay, so in quicksort, the majority of the work is therefore done in the partitioning, right? Similar to merge sort, where most of the work is done by merge, here most of the work is done by partition. So how do we partition an array. All right, so first of all, we just assume the pivot is stored at index low, right? So we're sorting between index low and high, so assume the pivot is stored at the leftmost index, which is low. Then we'll create two indexes, all right? So I, that's going to point to the start of the array, not including the pivot. So the reason we put the pivot at the start is so that it's out of the way of everything else. So we create an index to low plus 1. Then we create an index j to index high. So, if you can't visualize this in your head, we'll have an example right after this. Then what we're going to do is we're going to increment I until a of I is greater than the pivot, right? So we're scanning forwards through the array to find an element that doesn't belong on the left side of the array, right? So we find it, so we increment I until ai is greater than the pivot. Then we go to our other index and decrement that until we find an element that doesn't belong on the right side of the array, right? So we decrement j until aj is less than the pivot, right? And now we have two elements that don't belong where they are, don't belong on the sides that they're on at the moment. We swap them, right? So we swap the items at indices I and j, and then we just repeat that process until I and j meet in the middle, right, somewhere. And after I and j meet, we swap the pivot into the middle of the array, into index I or I plus 1. And I'll explain this in the example. All right, so let's jump to the example. So we're partitioning this array, and since 4 is the first element, 4 is chosen as the pivot. Right, so we are using 4 as the pivot. So what we do is we have two indexes, one to the start of the array and one to the end. And we're going to continue incrementing the left index while the element at that index is less than the pivot, right? So we start at 2, 2 is less than the pivot, so we increment it, and 7 is not less than the pivot. Right? So we stop incrementing the left index, and we move over to the right index, and now we decrement this index while the element is greater than the pivot. Right? So 5 is greater than the pivot, so we decrement, but 2 is not greater than the pivot. So now we've found an element which doesn't belong on the left side, and we found an element which doesn't belong on the right side. So what do? We swap the two elements. Right? So we swap them, and then we continue. So we repeat this until the indices meet. So we're going back to the left index, so we keep incrementing that until we find an element that is greater than pivot. Right? So 6. Then we go over to the right index, decrement that until we find an item that's less than the pivot. So that's 1. And then we swap them, right? And then we continue until the indices meet. So 1 is less than the pivot, so we'll move the left index forward, and finally the indices meet in the middle. Right, so after the indices meet, right, there are one of two possibilities, right? Either the element here is less than the pivot, less than or equal to the pivot, or the element here is greater than the pivot, right? So in this case, the element here is greater than the pivot. So what we want to do is we want the pivot to we want to move the pivot into the middle of the array, right? So we want to swap it with something, but we don't want to swap it with 6, right? Because if we swap the pivot with 6, then we'll have 6 on the left side of the 4, but 6 is greater than 4, right? So that would make sense. So what we do is we swap the item to the left of the 6 with the 4, right? So we get that. And now 4 is in the middle of the array. All the items to the left are smaller. All of the items to the right are greater. Right, and it says here, be careful. That's what I meant. Okay, and the partitioning is done. And notice that the left side of the array happens to be sorted, but that's not guaranteed, right? What you would do is you would then recursively quicksort the left half. Notice that the right half isn't sorted, right? So we would recursively quicksort that half as well. All right, so how about analyzing the partition operation? Right, so partitioning is O of n, right, where n is the number of elements being partitioned, so it's the number of elements in the part of the array that you're partitioning. And the reason it's On is because about n comparisons are performed. Right, you're going through each element, comparing it with the pivot, right, and at most n divided by 2 swaps are performed. Okay? So, what does the implementation look like? So, here's our naive quicksort function. Takes in an array, a low and a high. So here's the base case of quicksort, right? Similar to merge sort. If there's only one item in the array, then you return, right? Or if there are 0 items, then you return. Because an array with 1 item or 0 items is sorted. Now, what do we do next? We call the partition function, right? So we partition the array using the item at index low as our pivot. And the thing with partitioning is that we don't know where the pivot's going to end up, right? It could be in the middle, it could be somewhere near the beginning, it could be somewhere near the end of the array. So the partition function needs to return the index where the pivot ended up, right? Yes, question? So low and high are the beginning and end of the part of the array that you're sorting, because the function is recursive. So, you begin by calling the function on 0 and n minus 1, right, where n is the array size. But then when you recurse, you're calling, like when you recurse on the left side of the array, you're calling it on 0 and some index in the middle, right? So high will be some index between 0 and n. Yeah. Okay, so we get the index of the pivot, and then we call naive quicksort recursively and call it on the left side of the array, so that's between low and pivot index minus 1. And then we call it recursively on the right side of the array, which is between pivot index plus 1 and high. Okay? All right, so that's the quicksort function. How does the partition function work? So here's the partition function. Right, so first of all, we're going to figure out what our pivot is. So that's index low of our array. Then we create the 2 indexes I and j, like I described earlier. And then, so we have while true. So while true just means the loop's going to keep going until we break out of it. Right, so we have that. And the purposes of these 2 while loops is that, so the first while loop increments the left index until we find an item that doesn't belong on the left side of our array. Right? Then the second while loop decrements the right index until we find an item that doesn't belong on the right side of the array. Right? And then if I and j meet in the middle, then we break out of the loop. Otherwise, we swap the items at index I and j. Right? So that's, and then so index I and j are now the same, right? That's where the index is met. So here we just have that special case where if the indexes happen to meet at an element which is greater than the pivot, then you have to decrement I, right? Because, like as I showed earlier, right? Here, if the index is met where there's an element greater than pivot, then you want to swap the item to the left of it, right? Not the item at the index itself. Okay, so this if statement is just there to handle that. Then we swap index low with index I, right? So index low is where the pivot is stored, so we swap that into the middle of the array. Okay, then we return the index of the pivot. Okay. So now for the analysis of quicksort. So the best case of quicksort is O of n log n. So why is that? Well, in the ideal case, right, the pivot that we select ends up in the middle of the array, right, or near the middle. So what will happen is we have two roughly equal halves of the array, and we recursively quicksort each of them, right? So hopefully this diagram makes sense, where we recursively quicksort this half, we recursively quicksort this half, and then ideally the same thing happens on each of those arrays, right? So we have a good pivot here that splits the array roughly into half, and same on the right side, and the same thing just happens all the way down, right? So if that happens, then we'll end up with roughly log base 2n recursive levels, right? Similar to how merge sort has log base 2n recursive levels. And we know that across each level, so both of these recursive cores, and then there'll be 4 recursive cores under that. So on each level is going to require approximately n comparisons, right? Similar to how merge sort, across each level you have n comparisons when you're merging the arrays back together. Okay. So in this case, we get O of n log n, right? So what is the worst case of quicksort? Well, in the worst case, we get unlucky with the pivots that we choose, right? And we end up choosing the lowest or the highest value, right, for our pivot, right? And if we choose, so if we have an array and we choose the lowest value as our pivot, then we're going to end up with really uneven partitions, right? We'll get a partition of size 0, and we'll get a partition of size n-1, right? Hopefully you can see that in this diagram, right? So unfortunately here we've chosen the lowest value as our pivot, and now we have to recursively quicksort all of this, right? And if this keeps happening at every level, then we end up with n recursive levels, right? And each level is going to require only one less comparison than the level above, right? So this top level requires about n comparisons. The level below that is going to take about n-1 comparisons. The level under that is going to take about n-2 comparisons, and all the way down to 1 if we're really unlucky, right? So in total, the number of comparisons will end up being about n squared, right? So O of n squared is our worst case. All right, now for the average case. Well, it turns out that the average case is not the worst case, but it's n log n. And the reason for that is that if our array is randomly ordered, right, then the chance of repeatedly choosing a bad pivot is actually very low, right? And because if you have an array containing 10,000 numbers, well, what's the chance of choosing 0, then 1, then 2, then 3, and so on? That's really low, right? So yeah, on average, it turns out we'll get a complexity of about n log n. And we can show this empirically as well. So here, I've got a quicksort program. So if I just use the same commands as I used on Monday, so this will generate a sequence of random numbers, right, of 10 random numbers, and I'm going to pass it into the quicksort program. So in this case, I've called it naive quicksort. All right, so naive quicksort does work. So what happens if I increase the input size? So I'm going to go with 100,000 numbers, and I'm going to put time in front of the naive quicksort program. And since I don't care about the output, I'm going to redirect the outputs. So redirect all the numbers to dev null. Don't worry if you don't know what that means, but if I run it, I can see that it takes about 0.02 user time, right? 0.02 seconds user time. Okay. so hopefully you can see that a bit better now. All right, so that's a lot better than bubble sort or insertion sort, right? When I ran bubble sort on Monday, I think it took about 4 seconds for like 40,000 items or something like that. So we can see that quicksort is much faster than bubble sort. So what happens if I double the input size, right? Let's see how the time taken scales as I increase the input size. So if I double the input size, it takes about double the time, right? 0.04 seconds. What happens if I double it again? So it takes about 0.08 seconds, right? So it doubles again, and let's see what happens when I double it again to 800,000. It takes about 0.16 seconds, right? So from these timing results, it might seem like naive quicksort is linear, like ON, but it really isn't. It is ON log n, and the reason it looks linear is because if you look up a graph of n log n, it does look like very close to a straight line. So yeah, so you'll get timing results that look linear but really aren't. Okay. Okay. So yeah, that was just a demonstration to show the average case of quicksort. All right, so now for the properties of quicksort. So first of all, quicksort is unstable. Actually, I did not update this, but it is unstable because, not because of this reason, but it's because we perform long distance swaps, right? Long range swaps. All right, I did update this one. So quicksort is non-adaptive because, first of all, it has an average case of n log n, right? And if you think back to the definition of adaptive on Monday, it was a sorting algorithm is adaptive if it takes advantage of already sorted input, right? So if so the average case of quicksort is n log n, but if you give it sorted input, that doesn't improve it, right? It doesn't become ON or something. All right, and quicksort is in place, right? Because partitioning is done in place without using temporary arrays. And also to note that since quicksort is recursive, it uses stack space, right? So quicksort will use ON stack space in the worst case if you're really unlucky with your pivot selection. On average, it'll be O of log n stack space. Okay. All right. So quicksort. So there are some issues with quicksort, especially the one that I've shown you. So we've seen that the choice of the pivot that you select can have a significant effect on the runtime of the algorithm. Right? So the ideal pivot is the median value in the array, right? Because if you choose the median value as the pivot, right, then the pivot will end up in the middle of the array, and you have two very even partitions to sort, right? And you'll end up with an n log n runtime. Right, so that's the ideal pivot, but of course it's not possible for us to know what element is the pivot, right? So we just have to pick one and go with it. And if we always end up choosing the largest or smallest element as the pivot, then that will lead to the worst case, right, where it's ON squared. Right, so that means always picking the first or last element as the pivot, which is what the code I showed you before did, is not actually a good idea. Right? That's because if your input is ordered or reverse ordered, right, that's going to be a worst case that will lead to the function taking ON squared time. Right? And in practice, almost sorted data is actually quite common. So you wouldn't want to select the first element or last element as the pivot. Right? And this is what I've said before. So if you choose a bad pivot, then you'll end up with partitions of size n-1 and 0. And this pivot selection strategy is called naive quicksort. yeah, which is why, you know, here I named the program naive quicksort. Okay. So in order to combat this, we have different methods of selecting a pivot. All right, so the first one is called median of 3 partitioning. So in this partitioning method, instead of selecting the leftmost or rightmost element as the pivot, what we do is we look at 3 values. We look at the leftmost value, the middle value, and the rightmost value. And we pick the median of these 3 values as our pivot. All right, and if we do that, then ordered data is no longer our worst case, right? Because if our array is ordered, then we will end up selecting the middle value as the pivot, right? And the middle value will be the median, right, of the array. Right? So we'll get 2 very even partitions, and then we'll get a nice runtime. Right? So this does eliminate the worst case of, you know, sorted array and reverse sorted array, but it doesn't actually eliminate the worst case of O(n) squared completely. So it is possible to generate input such that the function is going to take O(n) squared time still. And you can try and think about how you could generate such an input. It's a fun exercise. But yeah, for real life data, it would make it much less likely to give you O(n) squared time. Okay, so the process is we look at index low, index high, and the midpoint, so index low plus high divided by 2, and we sort these 3 elements such that they're in order, right? So such that A at low is less than A at the midpoint, which is less than A at high, right? Then so that means after we've done the sorting, this element is the median of the 3 elements, right? So we swap this element with index low plus 1, right? So we swap the element with index low plus 1, and then we perform partitioning between index low plus 1 and high minus 1. All right, so when we partition, we don't need to include index low and index high, right? Because we already know that index low is less than the pivot, right? Whereas index high is greater than pivot because of the first step here, right? We sorted the 3 elements and then we picked the middle one. All right, so here's the code for median of 3 partitioning. Right, so with the quicksort function, we have our base case as normal, but then we call this median of 3 function. Right, so this function does what I explained in the previous slide. So we took the 3 elements, the left element, the right element, and the middle element, and sorted them. Right, so these 3 lines do that. Then we swap the middle index with index low plus 1. All right. Then we partition between index low plus 1 and index high minus 1. Right, so this is basically just this implements what I described here. Right, then we recursively quicksort the left half and the right half, just like with normal quicksort. All right, so that is median of 3 partitioning. Now, another method of partitioning is called randomized partitioning. And the idea here is we just pick a random value for the pivot, right? Just pick a random value. And if we do that, that makes it very hard to, it makes it very unlikely for O(n) squared performance to occur, right? Because if you select a random pivot, it's really unlikely for you to repeatedly select a bad pivot, right? Yeah, it is theoretically possible, but just very unlikely. Like, yeah, so the first version of quicksort that I showed has a worst case of O(n) squared, yeah. Yeah, so we select the random pivot, and yeah, that makes it impossible basically to generate inputs that would lead to O(n)² performance. Well, yeah, it is possible. Depending on what you enter, I think like maybe if your array has duplicates, then if your array has duplicates and the partitioning doesn't actually partition the duplicates properly, then you could get O(n)² performance. There are ways around that, but well, since it selects a random pivot, if the function takes a long time for that input once, it probably won't happen again because it selects a random pivot. Yeah. How's it quick? Well, that's a good question. It's just called quicksort. I'm not sure why it was called quicksort. But, well, is a question like why is it called quicksort? If it's best case is n log n, worst case is O(n)². I'm not sure why it's called quicksort. It's just called quicksort. Actually, we will discuss that. We will compare merge sort and quicksort at the end. But okay, so here's the implementation for randomized partitioning. So what goes on? So we have our base case as normal. Then we have this rand int function, right, which selects a random index between low and high. Right, and this just uses C's random number generation. So we swap this randomly chosen index with index low, so that our partition function can treat that element as our pivot. Right? Then we just recurse on the left side of the array, and then we recurse on the right side of the array. All right, so those were the two main pivot selection strategies, other than just selecting the first or last element. Right, so median of 3 and randomized partitioning. So what other ways can we improve quicksort? So one way is to use insertion sort. So the motivation behind this is when we have really small arrays, such as size 5 or less, then quicksort is actually going to take longer. It's going to perform more operations than a simple sorting algorithm like insertion sort. Right? And the reason is that quicksort uses recursion, right? And recursion, remember recursion, whenever you call a function recursively, it creates a stack frame for it, so that takes up some operations. So the idea is instead of recursing all the way down to 1 element with quicksort, we stop when the array has, say, less than 5 items. Right? So we handle small partitions with insertion sort. Right? And here is one way of implementing it. So we hash define a threshold, where if the size of the array is less than that, then we don't recurse any further, and we use insertion sort instead. Right? So here, if high minus low is less than threshold, then we call insertion sort between low and high, and then we return, and then this is just median of 3 partitioning. Right? So, yeah. Another way to implement this is instead of using insertion sort when the size of the part of the array is less than 5, you just return straight away. And then after the quicksort is done, you use insertion sort on the entire array. Right? So see here, we just run insertion sort once after the quicksort is done. All right, so now just a little bit of extra stuff. So quicksort on linked lists. So we can quicksort a linked list. Right? So the first step would be to pick an element as a pivot. Right? So you can pick the first element, or you can pick another element somewhere in the array, somewhere in the list, I mean. Then we create two empty lists, A and B, and for each element in the original list, if the element is less than the pivot, then we add it to list A. If the element is greater than the pivot, then we add it to list B. Then we recursively quicksort lists A and B. Right? And after that's done, we can form the sorted list by taking the list A that's been sorted, then adding the pivot after that, then adding sorted B after that. Okay. So now just comparing quicksort and merge sort a little bit. So we saw that the merge sort has a worst case, a best case, an average case of O of n log n, right? Whereas quicksort has a average case of n log n and a worst case of O n squared, right? So doesn't this mean that merge sort is better? So it turns out that due to how computers are designed, CPUs, it turns out that quicksort generally outperforms merge sort in real life use. Right? And the reason is that quicksort is more cache friendly. Right? So cache, not money, but it's spelled differently. So C-A-C-H-E. So cache, or sometimes it's pronounced cache. I'm not sure which one is right. But basically, memory, accessing RAM is relatively slow, right, in a computer. So it turns out that CPUs, most CPUs have a cache which stores, the bits of memory that have been recently accessed, right? And if you want to access the same region of memory again, then instead of going to RAM, you go to the cache, right, which is closer to the CPU, and that's much faster. So quicksort does exploit the cache, whereas merge sort doesn't exploit it as much, because merge sort uses a temporary array, right, which uses more, it has to allocate a separate block of memory when it merges the two sorted arrays together. Whereas quicksort doesn't do that, because quicksort is an in-place sort, right? It does the sorting within the original array. Yeah, question? So quicksort's more cache friendly because, well, first of all, merge sort, it mallocs a temporary array, right, when it does the merging. Right? Do you remember that? Yeah, so merge sort, it uses two arrays, right? Whereas quicksort, it only uses one array. When it's partitions, it does an in-place sort. Do you have a question? Yes, yeah, that'd be true. Yeah, on average it will. Yeah, so the question was, quicksort, will it use less memory compared to merge sort? And yes, on average it will. Yes, on the other hand, merge sort is stable, right? So quicksort is not stable, so if you want a stable sort, then you might want to go for merge sort. Merge sort is also easy to parallelize, right? And the reason is, with merge sort, you're evenly splitting the array into two halves, right? Whereas with quicksort, when you choose a pivot, you're not actually sure, where the pivot's going to end up. You might end up with a very small partition and a very large partition, and that's not as good if you're trying to parallelize it. Okay, and merge sort is also good for sorting linked lists. Okay, and that's because with quicksort, you're often accessing specific indexes of your array, right? If you have a linked list, it's hard to access a specific index, right? Because you can't just jump straight to it, you have to traverse the linked list, right? Yeah. Yeah, so quicksort, so there is a way to implement quicksort with linked lists. Yes, there is. Yeah. Okay, so that's it for quicksort. So now, before we move on, I think we'll take a 10-minute break, and then we'll get back to it. All right, so let's continue on. So this part of the lecture is going to be about non-comparison based sorts, but also a discussion of the n log n lower bounds for comparison based sorts. Okay, so all of these sorting algorithms we've covered so far have been comparison based sorts, right? Selection sort, bubble sort, insertion sort, shell sort, merge sort, quick sort. So all of these are comparison based sorts. What this means is that they work by comparing whole keys with each other, right? So given a way to compare two keys, these sorts can sort the entire array. It's like if you gave me, a bunch of potatoes and you asked me to sort them by weight and you gave me a scale, right? Using that scale, I can sort the potatoes by weight, right? And I can use any of the algorithms that we talked about, like bubble sort, selection sort, quick sort, whatever. All right, so knowing how to compare whole keys is all they need to be able to sort. Right, and what we can also show is that these algorithms, they require big omega of n log n comparisons. Right? This is probably the only time you'll see big omega in the course, but what it means is that basically they require at least k times n log n comparisons for some constant k. Okay, and why is that the case? Well, I'll try and explain it. It's possible that I completely botched the explanation, but I'll try. So suppose we have 3 items and we need to sort them. Right, so here I've just represented the items as circle, square, and triangle because we don't, because when a computer sorts items, right, it doesn't, it doesn't know, the relationship between the numbers. It just sees them as a series of zeros and ones. Right, so I'm just representing them abstractly with these shapes. So if we try to sort the 3 items, right, obviously just one comparison isn't sufficient to sort them, right? Because if we compare circle and square, well, that tells us how those 2 shapes are ordered, but it doesn't tell us anything about the triangle, right? So one comparison isn't enough. But also, even 2 comparisons isn't enough to sort them, right? So why is that the case? Well, if we have 3 items, right, then there are 3 factorial equals 6 ways to order them, right? There are 6 permutations of those items, and if the items are unique, then one of these permutations is sorted, right? And the other 5 are not sorted, and basically, a sorting algorithm, its job is to determine which one, right, is the sorted order. Right, so if we only get 2 comparisons, say we compare the circle with the square, then we compare the square with the triangle, then there are 4 combinations of results, right? So either they're both true, so circle is less than square and square is less than triangle, or they could be both false, so circle is not less than square and square is not less than triangle, or one of them is true and one of them is false, right? So circle is less than square, square is not less than triangle, or square is less than triangle, but circle is not less than square. Right, so we've got 6 possible permutations, one of which is the correct sorted order, and we got 4 possible combinations of results. Right? And what we can do is that each of these permutations, right, satisfies one of the combinations of results. Right? So if we find that both of these comparisons are true, so circle is less than square and square is less than triangle, then we can deduce that this is the correct sorted order. Right? So there's only one permutation that satisfies these two comparisons being true. Right? Now, if both of these comparisons are false, then there is also only one permutation that satisfies that. Right? So triangle, square, circle. But if one of the comparisons is true and one of them is false, then there are actually two permutations that satisfy, the comparison, one comparison being true and one comparison being false, right? So if it turns out that circle is less than square, but square is not less than triangle, which is this second column here, then one of these permutations is the correct sorted order, but there's no way for us to know which one unless we do one more comparison, right, between triangle and circle. Right? And similarly for if square is less than triangle, but circle is not less than square. Okay. So two possible permutations. Don't know which one. Yeah, question? Yes. Yeah, so, yeah. Did you have a question? Yeah.
As they have no number, try to make like circle smaller than square, and square smaller than triangle, and triangle smaller than circle.
So that would be a contradiction. So that wouldn't be possible. Like you wouldn't have like a rock, paper, scissors kind of thing. Sorry?
Something like greater than or equal to.
So I'm not sure what you're asking. Yeah. Yeah. Because they're transitive. Don't worry. Yeah. Okay. So, so mathematically, what do I actually mean? So if we have 3 items, then there are 3 factorial equals 6 ways to order them. So 6 permutations. But if we only perform 2 comparisons, then there are only 4 buckets, right? So these columns here I'm calling buckets to put the permutations in, right? And so that means at least one bucket is going to have more than one permutation in it, right? So here we have 4 buckets, but only 6 permutations. So they're going to have to double up, right? So we can't just sort numbers with 2 comparisons. We need at least 3 comparisons because this will create 8 buckets, right? 2 to the power of 3, right? So we'll have 8 combinations of results: true, 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 false, true, false, true, and so on. Yeah, question? It won't. If we have 8 buckets, then that means each permutation can sit in its own bucket, right? Yeah, you have 2 empty buckets. It might be, yeah, it could be. I need to think about it, but yeah. So 3 comparisons, then we have 8 buckets, so each permutation can sit in its own bucket, right? So now just zooming out, if we have n items, not just 3 items, then there are n factorial permutations, right? And if we perform k comparisons, that creates up to 2 to the k buckets, right? So given n items, the number of comparisons we have to do, k, such that we're able to have more buckets than number of permutations, right? That's going to satisfy this inequality, right? So 2 to the power of k, that's number of buckets. That has to be greater than or equal to n factorial, right? Which is number of permutations. So basically, we're trying to solve for k here. So there's just some involved math here to actually work it out. So you don't need to fully understand this, but I'll just talk you through it. So we need to find k such that 2 to the k is greater than or equal to n factorial. So if we take log base 2 of both sides, that gives us this. So log base 2 of 2 to the k is greater than or equal to log base 2 of n factorial. And since log base 2 of 2 to the k is k, we get that k is greater than or equal to log base 2 of n factorial. All right, and then there's something called Stirling's approximation, which I've linked in the slide. So if you click this, it will take you to a Wikipedia page on it. But log base 2 to log base 2 of n factorial, that's approximately equal to this expression here. So n log base 2n minus n log base 2e plus o plus big O of log base 2n. Right. Don't worry about this, you don't have to memorize it or anything. But if we remove the lower order terms, that gives us k is big omega of n log base 2n. Right. So this is basically just an informal proof that comparison-based sorts need at least n log n comparisons, or k times n log n comparisons. Yeah. Does k equal to n minus 1? No. So k is the number of comparisons that we need to perform. So maybe you can come ask me afterwards. Yeah. No, so it wouldn't be, but you can come and ask me after the lecture. All right, so therefore, the theoretical lower bound on worst case execution time for comparison-based sorts is big omega of n log n. All right, so this is basically saying that if you have a comparison-based sort, the worst case time complexity can't be better than n log n. Right? You can't do better than that. So then the question is, well, if we aren't just limited to comparing keys, can we achieve a better complexity than big O of n log n? Right, so it turns out that we can, and these algorithms are called non-comparison based sorting algorithms. And the way they achieve a better complexity than n log n is that they exploit specific properties of the data, right, to sort it. Yes. So I'm going to show you guys just one non-comparison based sorting algorithm, which is called radix sort. All right, so radix sort is non-comparison based, and what it requires is we need to be able to decompose our keys into individual symbols, like digits, characters, bits, or so on. Right, for example, the key 372, that would be decomposed into 372, so those would be our digits. The key Sydney, so there's a string, will be decomposed into the characters S, Y, D, and E, Y. Right, so we decompose our keys into individual symbols. And formally, each key K is decomposed into a tuple, or a tuple, K1, K2, K3, so on up to Km. So M is the number of, is like the width of our key, right? The number of symbols that make up our key. Right, so for 372, M would be 3, right, because there are 3 digits. For Sydney, M would be 6, because there are 6 letters. All right, so other requirements of radix sort. So ideally, the range of possible symbols is relatively small. Okay, so for example, if our keys are numeric, then the digits are between 0 and 9, right? If we're dealing with base 10 numbers, right? If you're dealing with base 16, then it would be from 0 to 9, then you have A to F, so it would be 16 possible symbols, and that's relatively small, right? If we're dealing with alphabetic strings, then we would have 26 possible symbols, right? That's also a relatively small amount. Okay, and why is radix sort called radix sort? Well, the reason is the number of possible symbols, that's known as the radix, right? And we denote this by R. So for numeric, R would be equal to 10, right? Because you've got digits from 0 to 9. For alphabetic keys, R would be 26, right? Because you've got 26 letters of the alphabet. All right, and radix sort also requires keys to have the same length, right? So if you have keys of different length, for example, 123, that's 3 digits, and you have 15, which is 2 digits, then you would pad the 15 with a leading 0, right? So 15 would be represented by 0, 1, 5. Right? The number 7 would be padded so that it's 0, 0, 7. Okay? And if you have alphabetic keys, then you would pad the shorter strings with a blank, with a trailing blank. Right? So Z, Z blank, or if your key is just a T, then if your longest key has 3 letters, then you'd pad the T with 2 blanks, right? So T blank blank. All right. So what is the method behind radix sort? Well, the method is we perform a stable sort on Km. So Km is the last symbol of the key. Right, then we perform a stable sort on Km-1, that's the second last symbol of the key. Then we keep going, and finally we perform a stable sort on K1. So K1 is the first symbol of the key. Right, so here's an example of radix sort. Right, so we have a bunch of words containing 3 letters. Right, so the way we would sort this with radix sort is that we perform a stable sort on the 3rd character, right, on the 3rd character. Then we perform a stable sort on the 2nd character. Then we perform a stable sort on the 1st character. Okay, and if you're thinking, why do we, perform a stable sort, starting from the last character? Think back to the example I showed you on Monday's lecture, where we're sorting an array of names, right? Where we had first names and last names, right? If we want to sort the array such that the first names are ordered, but if the first names are the same, then the last names are ordered, then you have to sort by last name first and then by first name, right? So similar to that. Okay, so here's the pseudocode for radix sort. Actually, before we go to that, you might be wondering, okay, so I said that radix sort is a non-comparison based sort, so it can help us achieve a time complexity of better than n log n, right? So so how do we do the stable sorts, on each character, right? So here we have to perform a stable sort on the 3rd character, but how do I do that, right? If I use merge sort, then that's going to be n log n, right? And if I use bubble sort, then it might be as bad as n squared. So how do we actually do the sorts, do the stable sort, right, while still being not as bad as n log n? So this is how radix sort does it, right? And it relies on the fact that the range of possible symbols is reasonably small, right? And what radix sort does is it creates one bucket for each symbol, right? For each possible symbol. So if our input is alphabetic, then radix sort will create 26 buckets, right? One for each letter. It will also create one. It might also create one bucket for the blank character, because I said that you have to pad your keys if they're too short. Right. So in radix sort, so we have an array A of keys where each key consists of m symbols, right? So m is the length of your keys. Then radix sort will initialize m buckets, right? One for each symbol. And then we have a loop where we loop from m down to 1, right? The purpose of this is because we want to sort by the last symbol first, then the second last symbol, then the third last symbol, then at the end we want to sort by the first symbol. Right, so I will show you an example of this right after this, in case you're confused. But inside the loop, we empty all the buckets because during the loop we will fill the buckets. So we empty the buckets first. Then for each key in the array, we append the key to bucket key I. Right, so key I, so this is the ith symbol in the key. Right, and don't worry if you're confused, I will show you a visualization of this. So for every key, we append that key to the corresponding bucket, and then we clear the array. Right, so we clear the array. Then for each bucket in order, so we would, if our keys were alphabetic, then we would start at bucket A, then bucket B, then bucket C, and so on. So for each bucket and for each key inside that bucket, we append the key to the array. Right, and that's all we do. And I have an example coming up. Do you have a question? You can, yeah. You can use a linked list. Yeah, so bucket here I've described it very abstractly, and there are different ways you can implement a bucket. But one way would be to use a linked list. Another way would be to use an array that's capable of resizing, because you don't necessarily know how many keys will be stored in each bucket beforehand. We can discuss this afterwards. Yeah. All right. So here's the example. So suppose the alphabet is just A, B, C. All right. So just because this is an example, I don't want to create too many buckets, draw too many buckets in the diagram. So we have 3 letters A, B, C. So R, our radix is 3, and we want to sort this array. Right. So since the strings have different lengths, we first have to pad the shorter keys with the blank characters. So A would have 2 blanks after it. CA would have 1 blank after it. And in this case, M is 3, right? M is the length of a key, right? The number of symbols in a key. Right? So now here is, so here are all the buckets that radix sort's going to create. So it's going to create one for each letter, A, B, C. It's also going to create a bucket for the blank character. Right? And what happens first? Well, radix sort first sorts by the last character in each key. Right? So the last characters are C, B, A, blank, blank. Right? So now for each key in the array, it's going to store that key into the corresponding bucket. Right? So the last character here is C, so we store that in the C bucket. Right? So for cab, the last symbol is B, so we store this in the B bucket. BAA, right, that ends with the A symbol, so we store that in the A bucket. Right, A blank blank, the last symbol is blank, so we store that in the blank bucket. And CA blank ends with blank, so we store this in the blank bucket. Okay? So we assume here that storing a key into a bucket takes O1 time, constant time. Right? So now that we've stored all the elements into the buckets, we clear our array. And then for all the buckets in order, we store them back into the array. Right? So this blank bucket contains these 2 keys, so we store them into the array. Boom, boom. Then the next bucket contains BAA, so we store that into the array. Then this bucket, we store that into the array. Then we store this into the array. And now we've sorted the keys by their last character, right? And we've done this in basically linear time. So it wasn't n log n, it's linear time because we have these buckets, right? Okay, so the next step is we want to sort the array by the second character in each key, right? So the second characters are blank, A, B. Right, so for the first key, we store this in the blank bucket, then we store this in the A bucket, we store this in the A bucket, we store this in the A bucket, and we store this in the B bucket, okay? And then, once again, we clear our array, and then store these elements or store these keys back into the array, right, in order. So we store this, then for the A bucket we store these into the array in order, then for B we store this into the array. Okay. So now we've sorted by the second character, or the second symbol, and C bucket is empty. Right. So next, we want to sort by the first character. Right. So this goes in the A bucket, this goes in the C bucket, this goes in the B bucket, this goes in the C bucket, and this goes in the A bucket. All right. And now, again, we clear the array and store these keys back into the array in order. Right, so the blank bucket is empty. The A bucket, we store these back into the array. The B bucket, we store that into the array. And the C bucket, we store these into the array. And the result is that we have sorted the keys, right, in alphabetical order. All right, so that's how radical sort works. And note that we didn't need to perform any comparisons between keys, right? Okay, so here's the analysis of radical sort. So we know that the array contains n keys, right? That's the size of the array. Do you have a question? Sorry? Yes. Yeah, we're sorting 3 times, yes. Yeah, so, all right, so the array contains n keys. Each key contains m symbols, right? And the radical sort uses r buckets, right? Actually, here it uses 4 buckets, not 3, but r plus 1, you know, close enough. Radical sort uses r buckets, a single stable sort. So one of the sorts runs in time n plus r, right? So why does it run in time n plus r? That's because we store all the keys into the buckets. That takes O(n) time. Right, then we need to loop through the buckets. That takes O of r time, and store the keys back into the array, right, which is O(n) time. So O(n) plus r. And radical sort performs the stable sort m times, right? 1 for each symbol in the key. So the time complexity for radical sort is big O of m times n plus r. Okay, and assuming that r is relatively small, like 26 for alphabetic keys or 10 for numeric keys, then this is approximately equal to big O of m times n, right? Okay, so what does this mean? Well, radical sort will perform better than comparison-based sorting algorithms when the keys are short, which is when m is small, right, and arrays are large, right? That's because what's the best that you can do with comparison-based sorting algorithms? It's n log n, right? So if we know that m is going to be smaller than log n, then comparison-based sorting algorithms may perform better. Okay, so now what are the properties of radical sort? So radical sort is stable, right? Why is it stable? That's because all the sorts that we do in the algorithm, all the subsorts, I've called them, they're stable, right? So that means radical sort itself will be stable. How about adaptivity? So yeah. Is radical sort adaptive? No, it's not. Right? That's because it performs the same steps regardless of the sortedness of the array. And radical sort is definitely not in place. Right? That's because it uses additional space for the buckets. Right? It stores the elements into the buckets. Right? So it's definitely not in place. So it uses big O of r plus n additional space. Right? R, remember, is the radix, so that's the number of buckets. N is the number of items in the array. Right, so it uses this much space for buckets and storing keys in buckets. All right, so that was radical sort. And now here are some other non-comparison based sorts for your curiosity. And so there is something called bucket sort. Right, there are actually two versions of radix sort. Right, so the version that I showed you was called LSD radix sort, least significant digits. I think that's what it stands for. There's also a version of radix sort called MSD, most significant digit. And what it does is instead of sorting by the last digit first, the last symbol first, it sorts by the first symbol. Right, so yeah, you can look into this if you're curious. There's also key index counting sort, so this is for sorting small integers. And there are other non-comparison based sorts. But that's all I wanted to show you in terms of non-comparison based sorts. And since we're done, I think we can end the lecture here and you can have an early break. All right. Okay, so I'll see you guys next week. Have a good week.